Welcome. So, this is on yet another interesting topic. So, what we are going to do is use the adversarial autoencoder network which we had learnt in the previous lecture in order to even build up a classifier. So, this is what I was telling you in the previous lecture, that what we have been doing till now in that example was basically to use these networks in order to generate out synthetic samples. Now, it is good to generate out synthetic examples, because now you can really augment out your data set with these kind of examples going down over there. Now, the question still remains that can I make a classifier network robust to these kind of adversarial examples, which means that I can have unknown examples, unknown types of examples which comes from, because from your adversarial learning what exactly happens is that you have some discrete points around on your feature space over there which are spread out around everywhere, and then you are going to pull out from one point over here on the Gaussian, and you model this as a Gaussian network over there, and then now that you are pulling out these random points over there and pass it through the decoder network, you have some sort of an image being generated. That is straightforward what you are doing now. Now, the question which comes out over here on the adversarial autoencoder for classification is that instead of trying to use all of those synthetic examples which I have generated, can I use this encoder block over here in order to train a network, and is this assumption valid that the classification network which is built up on top of using this encoder block on the autoencoder is going to be robust. So, this is the straight question which we are going to answer in this particular lecture over there. Now, the first part of it is just to look down into your standard usable routines and header files over there. We are just going to make use of them. Now, from there the second part of it is to load down your data set and have your data loader ready. So, this is where we do not make any change as such coming down from whatever was there in the earlier lecture. So, it is pretty simple. So, let me just run each block over there as I keep on moving down. So, now on my data set, let us run it. So, you have your data set loaded down, and then you have your these extra variables on NumPy conversion as well as extra functions on NumPy conversion or to conversion to an autograd variable, and on converting it down to a CUDA. Now, once that is done, we define our network over here. So, the network is quite simple and straightforward, and it is the same network which we had done in the earlier lecture number 54, where we were trying to generate out synthetic examples. Now, so we write it down in a very generic format, such that you can take any number of inputs on your any number of input neurons on your side over there, and then pass it through this network in order to get down your latent variable or the hidden variable space over there. And the hidden variable space is something which you can change based on how you would like to do it, and the total number of hidden layers over there and the number of neurons in the hidden layer is what you are going to keep it out straightforward. So, that is how this model is going to work out, and then whether to choose and have dropout or not is up to you, and we are sticking down to the same exactly the same network. We are not making any change over there. Okay. So, now you have your encoder defined, you have your decoder which is also defined in the similar way, and then you have your discriminator for your real versus fake discrimination over there. So, this is also defined in the same way as it was done in the previous lecture, and we are not going to make any changes on that one. Now, in order to define your optimizer, so let us see, yes, that has run and I am ready. So, in order to define your optimizer, this is where I make a few changes coming down. So, one is this important part over there. So, your z dimensions in the earlier case was just limited down to 2 variables over there. So, you had a 2D random number being generated out of this latent variable space. Now, this is what we have changed it down and made it down to 100, and one of the reasons for changing it from 2 to 100 was, if you closely recall from our experiments in using autoencoders in order to classify these digits in MNIST, then we did realize that if you have lesser number of neurons in a given layer, and there is a significant bottlenecking which happens over there, your reconstruction quality is affected, but on the other side of it, you are going to squeeze out and compress all of these features so much that trying to classify out with these features also becomes really problematic. So, essentially what we have to do is we need to retain say an over complete representation of these features which comes out over there, and for that particular reason, instead of taking this latent variable space as just a 2D tensor over there, I am going to take this as a 100D tensor. So, this is the only change. So, definitely for that reason In the earlier case where you could vary down from -1 to +1 in uniform intervals, and you get down some 100 random values, and that helps you in order to synthesize images over there. So here it's no more possible because it's 100 dimension. Now trying to visualize anything beyond 3 dimensions is definitely problematic. I mean, you can add color and maybe visualize a 4th dimension, but it's seriously problematic to go up to say 100 dimensions over there in any way. So that's where we don't make use of in that way, but I will exactly show you a bit later down as to the advantage which you get down when you do it with 100 dimensions, and how can you still pull out some random values on this 100 dimensional vector in order to show your synthetic samples which are generated. Okay. So let's run this part while I go down through the rest of it. Now for my network, which is my encoder over there, it's plain straightforward and similar to the earlier one. You have 1000 neurons in your hidden layer over there. The only change which comes down is that you have 100 neurons in your bottleneck layer present over there. So similarly comes down your decoder, which has a similar kind of a configuration, and your discriminator over there, which also has a similar kind of a configuration. So we are not changing anything. The only thing which changes in the discriminator is that my number of neurons in the hidden layer is no more as 1000, but this number of neurons over there is just 500 present over there. So and this is alike what we had in the earlier lecture as well. Okay. Now for the generator and the so for two of them, one is the generation learning rate, another is the regularization learning rate. So what this basically means is that in one pass of it, you are going to do a forward propagation over your encoder decoder network. In the next pass, you are going to do a back propagation over your discriminator and a back propagation over your encoder as well. So for these two, we are setting down two different learning rates over there, and that's to keep it conformal to the dynamic range of the gradients which get on generated over there. Okay. So that's the only point over here, and then you have your two optimizers set down for the two different passes over the network. So once done, so we have our test data which is being generated. Now in the earlier case, if you remember, our test data was something which was sampled out in the range of -1 to +1 in 2 dimensions over there on a uniform sampling. Now here I don't have that option of doing it because it's a 100 dimensional variable. So what I essentially end up doing is that I sample out some random 100 numbers on a 100 dimensional space which exist on a Gaussian distribution. So you can have a multivariate Gaussian distribution. So here we choose to have the total number of variables as 100 in this distribution, from where I would like to pull out these numbers. So I pull out some 100 random numbers from a 100 dimensional Gaussian distribution used over here. Okay. So that gets me my test data created. So now after that I start my training process over here. So that's the straightforward training process which I have over there, and in which you do your first pass over the network for your encoder to decoder, and then the second pass is where you are going to train your discriminator and also update your encoder part of the network. And now the loss functions which we take over here are binary cross entropy for both of them. Now for a very simple reason that say your discriminator anyways is going to pull out 0 and 1, which is fake or real over there, but then your encoder over there, whatever it produces, it's in a range of 0 to 1. So on these MNIST, you clearly remember that your background was all black and your digit was written down in white, or say vice versa, whichever way you want to take it up. So anyways, this is the one versus the other class 0-1 classification, and binary cross entropy is definitely a good way of working out on this network over there. So let's get this part of it running as well. So I have run till optimizer. So let's initialize out the test data, and then I get this one running while we look into how it works out as well. Now the rest part of the problem is pretty straightforward. So there is no major change which comes down in the routine over there, except for the fact that here we are not going to train it down over a lot number of epochs. We just going to train it down over 50 number of epochs, and that's so the change which comes over here is that since your latent variable is no more 2 or not much squeezed out over there, so you can actually have an overcomplete representation in this intermediate layer. Now that you have a over complete representation in this intermediate layer, so there is not much of information loss which happens, and since there is lesser amount of information loss which as such can happen down over there, so with lesser number of epochs you will actually be starting to look out at a convergence point. So we are just looking down at 50 epochs over here in order to come down closer to a convergence point. And so as it keeps on training over here, you would be seeing these are the kind of images which keep on getting generated. So at the initial part over there, you would see these things which look like 3, and then there are a bit of these which are noisy, and eventually this would, like, some of them would start taking up the figure of an 8, some of them will still be looking down a 3, something which looks like almost a 0 but not exactly a 0, some of them start looking like 9, and these are the different varieties which it comes on creating. Now this is at the initial stage of it, and as it keeps on getting updated, sometimes in certain epochs you would see that it completely washes out, and there are no distinct ones. So in the earlier epoch you could see out some certain figures, but here I am not able to see out any distinct figures which keep on coming out. Now that's a part of the generative model itself, because it's a gameplay which is happening. So once your encoder decoder is trying to optimize itself, then there will be some sort of a shift in this latent variable distribution. Then while you are trying to train your discriminator, you are again going to enforce that these two come down closer to each other, and in this whole process that these two distributions start mimicking each other, which means that the latent variable starts mimicking the random value distribution from where you are drawing samples, you are going to update the encoder. Now that this encoder weights has changed, so the decoder also has to learn itself, and then this keeps on going on and on. So that's what you essentially keep on seeing over here. Now this might take some time. Yeah, so now it has run down for 50 epochs, and this is what we have over here. Now from a generative principle, it does not look that clean and clear. You can but this is just for the sake of the lectures which we are doing over here, that we would try to minimize the amount of time needed. Now typically what I would suggest is that keep on running this for about 1000 epochs when you start looking at very exact looking numbers created out over there, and then the generator actually is something which is converging, and your encoded decoder over there has also learnt out robust weights. Okay. So now let us get into the classifier over here in order to see what happens. So now the whole objective is that I have my autoencoder which was trained out. So I had an encoder, decoder, and I had a discriminator. But now what I am telling is that instead of trying to use these synthetic examples in order to train a classification model, can I use this encoder block alone in order to use a classification model? Now we have done our lectures on domain adaptation. We have known how to actually transfer a pre-trained model, an existing model, onto a newer kind of a mechanism where you can actually modify the architecture over there as you go on. So that's what we are going to do over here as well. So this is a plain simple domain adaptation thing which we are going to solve out. So here what we do is we take this network Q, or which is that encoder which we had defined earlier. So let's go up. So you have this QNet over here, which is my encoder block which was defined. So what I am trying to do over here is create a new neural network in which the first part is just this Q, or the encoder block which was defined. Now the output of that encoder block has 100 neurons being thrown out, and if I am trying to solve a MNIST digit classification problem, then I have 10 classes. It is 0 to 9 numbers over there, which is just 10 classes. So I will create a separate part of the network which will have just connection between 100 neurons onto 10 neurons, and this is my final classification. And on the forward pass, what we are going to do is you do a forward pass over this Q to get down your latent representation. From that 100, you do a forward pass over the next fully connected layer onto 10 neurons over there. So that's my definition for the classifier which is created over here. Okay. Now if I have my CUDA available, I can just convert it onto my CUDA system over there. So that works out over here, and then I start defining my criterion functions. Now here, instead of using binary cross entropy, we are going to use the cross entropy loss, because this is a multi-hot vector which comes out over there, and the optimizer which we use for this purpose is also Adam with its own specific learning rate. Okay. Now starts down the training for 10 number of epochs. So the reason why we need to train is, one way in which you can train this one is you preserve down the encoder part over there and just update the classifier part. So that's a frozen mechanism of training and doing a domain adaptation. The other mechanism of doing is where you have an end-to-end training. So, we are going to use the later mechanism in which you do an end-to-end update of all the weights within your network, including your encoder and then your fully connected network over there. We train it over 10 iterations, and that is how it keeps on going. So, the first part is where you have your data being converted onto variables or autograd variables over there. Then you start your training routine, and within your training routine you are going to zero down your gradients and find out your output over there, find out your loss, and then do a nabla of loss over there. Now, once that is done, now you can do your optimizer dot step, or which is just a backpropagation update routine and the weight update equations which come into play. So, this is for my training part over there. Now, as I keep on training, I also try to look into my testing mechanism over here, and this is for my testing. So, let me just run these rest of the modules over here. So, I have my classification network defined, I have it typecasted, and this is what is printed out, and you can pretty much see what it looks like. So, this is that first part of it, which is my encoder part, and then you have this. So, this part is my encoder part over there, and then I have my classification which is brought out over here. Then I run my optimizer and my criterion function, and then I can set my training module running down over there. Now, this won't be taking much of a time because you straightforward are just doing it for 10 number of iterations over there, and the network which you have as such in your encoder to decoder is still a much smaller network to go down, except for the fact that this encoder is now trained down to be much more robust to a large number of unknown and unseen samples. However, the challenge still is that whatever examples you have seen down over there being generated out through this adversarial process, they are not that wide, because we could not train it down for a large number of epochs. We had just trained it down for some 50 epochs over there, or 50 iterations, and now within this 50 epochs you do not tend to technically get down a faster convergence coming down anyway. You keep on training that part for 1000 iterations in the first part when you are trying to build your adversarial autoencoder. Then the encoder which you build over there is a really robust one, and taking that encoder as an initial point in order to build your classified is definitely going to work out pretty good. So, now this part of my training has run down for 10 number of iterations, and if you look at it, it starts with the initial accuracy of 92.6%, and then somewhere around the 10th epoch it's already at an accuracy of 98%. Now, if you recall back from your autoencoder strategies where you were just using an autoencoder in order to classify it out, it was really hard for you to go down to that accuracy level of a 98%. So, we were with an autoencoder we were somewhere reaching a saturation of accuracy of 93 to 94%. Now, the moment we have this adversarial mechanism, because it starts becoming robust to all of these unknown examples which it had not seen earlier. So, this performance actually starts growing out in a big way. So, this is one of these beauties of trying to use an adversarial network in order to initialize. The number of features which you learn and the gamut of features which you learn is much more richer and wider in order to train a classification network over there. And it is not necessary that you need to have synthetic samples generated out over there and then train another network. In fact, the synthetic sample generating network itself can also be used for training a classifier in its own way. So, that is where we come to an end for this particular lecture on adversarial autoencoders and trying to use these adversarial mechanisms in order to train a classifier as well. So, till then we come to a conclusion for this particular week with generative models, and next week we are going to enter into another interesting module which is on trying to understand and analyze videos, which we haven't done till now. So, that is where your data structure is quite different, and the way you would be representing all of these data in terms of a tensor and what happens to your channels, batch numbers and everything is an interesting fact to play on. So, stay tuned till the next week, and till then goodbye.